So thank you all for coming. I know it's late in the last day, so I appreciate the attendance and the paying attention to Fred and I. Talk about some more leak detection and, no, not leak detection. This is liquid cooling integration and
Switching
logistics.
gears.
Yeah, does have to do with some leak detection though, but this is good. So I'm Matt Archibald, Director of Technical Architecture for nVent and responsible for our liquid cooling and our overall data center and networking business. Dealt with a lot of installs over the past 8 to 10 years with liquid cooling. Came from the IT manufacturer space, so have some background in what tests need to be done at the at the server level prior to shipping, how that integration happens. Previous employer did sell a lot of integrated systems. Current employer sells infrastructure that supports those systems, so have knowledge on both sides of it, and then going outward into the rest of the till you about leave the rack, and that's what we're really focused on here is the rack.
Great. I'm Fred Rebarber with Vertiv. I work in our thermal business. I've been involved in a lot of liquid cooling projects, some interesting ones, and so I'll tell a few stories as we go through the presentation here on a couple of the projects that I've worked on, and it'll help the story.
Cool. Yeah, so what this presentation came out of another white paper that was written really about liquid cooling integration and logistics, so dealing with the shipping, integrated rack and liquid cooled systems ready for deployment or at least commissioning at various stages and the considerations therein. It is a bit of a lengthy white paper, 24 pages, but that's just because there can be so many different directions that this can go. So we're going to give a bit of an overview of the paper, highlight some of the important pieces, encourage you to go out there and read it and take a look and get into it. So you hit the nail on the head one more time here. Why liquid cooling? Really, our driving factor of this is at face value. I think liquid cooling can be a terrific enabler of the highest performance you can get out of computing. It's been in the HPC space for many years. It's been around for almost 60 years in the high-end and mainframe systems that we'll call it liquid cooling, but it could be refrigerant based. A lot of that. So there's a lot of benefits, and we discussed in the previous presentation the risks and rewards on the leak detection, but the rewards that it enable are there. So now what our focus is on from a vendor perspective, from an integration perspective, and from an end user perspective. What all has to go into that, what checks should be done, and how all that could potentially work going through it.
Yeah, when you compare, the air-cooled systems and the liquid-cooled systems, there's a lot of things to consider when you're going through the whole process of, assembling the rack, installing the cold plates, and their delivery points and where it's going. And then even when you get to the data center, the whole commissioning side of things and things you have to take into account are really not that obvious when it comes to, implying, say, even a liquid load bank. And some of the steps you have to do to make sure that when you implement a liquid load bank that your source is clean and you're not contaminating the system. So I think, as you go through the paper, keep in mind that we're trying to cover from where the rack is manufactured and where the system is put together to the transport all the way through the data center and commissioning. So I think it'll be
decommissioning.
That's
another big one that, okay, that's great. You got water or liquid cooled in your IT and you're working, but then you have to remove it. And that can be just as complex as installing it. We touch on this, and Fred really hit this home. It's not as simple as it sounds, like assembling, inserting memory drives, I/O cards, server board. You wrap that in a chassis. You put that chassis in a rack. You cable it. You have your power infrastructure. You're ready to go. When that arrives on site, in the air-cooled space, what do you really have to do? Apply power. Nothing's really going to be problematic with that because your fans will come up, your system should be fairly cooled, and you're ready to go. Liquid cooling is a lot more complex than that because you don't just want to ship a dry system to an end user and say, okay, I'm ready to go. you have to apply some level of liquid before you can apply power. And you want to know that through the entire build process, the components that you've used, the sub-assemblies, have been checked, have been verified. They've been verified as a system, down through the manifolds, down through the quick disconnects, hoses, connections to the facilities that we just talked about. There's a lot of emphasis and work on connections. How all that works, because the last thing you want to do is just throw some water into it and have a leak before you've ever powered it on. And I've dealt with that. It's not fun. It's not fun to fix. And, the story that John Gross told about, having to take a week and a half to, ultrasound all the welds that particular welder went through and did. I wish it was a week and a half in the time that I had to deal with it. It was like 6 weeks, and it was painful. And there was a lot of work to be done, and it wasn't easy. And that delays uptime, that delays deployment, handing the keys over to the customer. So there's a lot more involved, and there can be many different levels of this. We talked about before, we have refrigerant, we have dielectrics, we have water-based, there are negative pressure, there are other things that affect all of these that go into it. So this was meant to be generic. It was meant to be as encompassing as we could possibly think about. We clearly have missed some things somewhere along the way, but please tell us. This is Rev 1. We're more open to updating it as we go forward, but yeah, tell us give us your input.
Yeah, and you'll see a number of the steps that we talk about, and I would say that it's a system, right? So, and in a couple of recent commissioning jobs that we did, there's processes that are built in there to, one, check each step of the way. So you're going to want to make sure that your manifolds are clean, your pipes are clean. There were some comments that I saw in the previous presentation about cleanliness of pipes, really critical. I had a customer call and say, Fred, your CDU unit is not performing to the capacity that it should be. And at the end of the cut to the chase, we actually cut the unit out, pulled the heat exchangers out, and found that there was debris in the piping system. The contractor hadn't flushed the whole system, and it was sitting for a while. So, even before the unit gets there and you install it, you have to make sure that what you're connecting to is not going to give any contamination to the system, to the CDU or down into the cold plates for sure.
Yeah, and there's some connector vendors in the audience, so that as much as the cold plates and the heat exchangers have those tight tolerances, the poppets on the QDs, those there also can really be affected, especially when you go to either service a node in a blind mate. When you pull that node out and all of a sudden water's, how much is a problem? Is a drip a problem? Probably not, but is a spray a problem? It is a pressurized system. So there are those issues, and there's other ways, other technologies that can mitigate that and things to worry about. So, we get into this, and we're going to come back and see this chart, but we're basically going to step through each one of these columns here and essentially detail at a really, really high level, because there is so much detail in this paper, but at a really high level, the four main categories of start to finish of not just the system design, but really we assume that the system is designed. We assume that there is a cold plate with loops, with hoses that has made its way out of the server. That has to be integrated at the server. We'll call that manufacture. What we define as L1 through L10 is essentially the server build process, or the ITE build process, integration of the liquid cold plate loop. And we know there's other technologies out there, but the focus of this paper was limited to, a liquid cold plates within ITE connected to rack-based manifolds connected to CDUs. We know that there's a whole bunch of different iterations to that. We'll work on addressing those as we go forward, but if you see the white paper, you see there's a lot of detail in there. And then we talk about L11 and L12, which is the rack itself integrated with the ITE, with the manifolds added into it, with hoses leaving it, going to a CDU or somewhere else. We'll call that the facility. So all these things, from the manufacturing, the steps involved in that, the transport of those. You could have the ITE transported separately than the rack and the manifolds. That could all be integrated in one position. It could be integrated by select manufacturers that have multiple components to provide and then shipped. So there's a lot of different deviations between there. And then you get to the integration step. Okay, now it's a network, it's a system. What do you do? And then finally, you get to the deploy. And as mentioned before, deploying isn't just, hey, throw some water in it and let it go. Deploying is you've got to test it for that safety assurance before you put it on. What does that look like? And then decommissioning. That's often overlooked because you're so happy to get it in and running in your data center. But when you go to decommission, air-cooled is real easy. You put it on the truck and away it goes to a recycler to figure that out. Liquid's a little bit different. You've got to drain it. You're typically dealing with, either if it's refrigerant that Fred has a lot of background with, or if it's treated water, you can't just necessarily dump that wherever. If it's propylene glycol, it's got to be handled safely. So, and disposed of safely. So it does add another element to that. So we'll step through each one of these as we go, but anything on top of that?
Yeah, the processes here covering, the build of the system out through, getting it installed. I would add that there's a whole nother step when you hear the, L process. For the other of you who are on the facility side, you might be also familiar with, commissioning steps of L3, L4, and L5. So don't get those confused with this process. And in the commissioning process, L3 is startup, and then it runs through L4 and L5, which is actually functional test, and then integrating the building management systems. So a little different test, but once you get it to that stage where you're integrated into the building, that'll also exercise the system. We're going to talk, the paper goes through more details on when you're shipping the products and some of the gases that might be used during transportation. So there's a lot of those things that you have to consider once the rack arrives to your data center and you need to implement.
Yep. Yeah, so let's jump into a little more of that. What do these different L levels mean for the server manufacturing or ITE manufacturing, and then the L11 and L12 for the rack integration. We're not going to define them here in this presentation. They are covered within the paper, spelled out fairly clearly. And we did solicit input from the different ITE vendors to make sure that's correct, get their input on that, and just sort of say to them, so how would you do it? Adding liquid cold plate loops, how would you do it? What would you be looking for? What's important? So from, I think, the high level at the manufacturing standpoint is when you get to the sort of L10 level, you're ready to integrate the cold plate loops in there. It's sort of the final thing that's done. From an ITE vendor, you would be looking at, the test reports that come from that cold plate and cold plate loop vendor. How are they shipped? Are they filled with liquid? That could be a possibility. Are they filled with a pressurized gas? That could be a possibility. And what checks you have to do to ensure that just the products that you've received are functional. You can't exactly, without a full test fixture, you can't exactly just power these things up to see that they work. And you don't necessarily want to charge them with too much pressure because that could cause other issues. But there is a bit of planning that you have to do. There has to be some level of ITE level box line or end line manufacturing testing that you will most likely need to flow some level of liquid through each node for solution and quality assurance. A lot of that is then, okay, we've done everything powers up, we're good to go on to the next. And that's a decision on the integrator and the end customer. Do they want their cold plate loop shipped with liquid in it, or don't they? What liquid is that? If it's PG, you can operate, we would say, with shipping and logistics in a bit cooler of a temperature, but not necessarily the minus 40 to 80 that the IT is sort of spec'd at. If you're treated water, you're certainly probably not going to go much below 36 or 32 Fahrenheit for the risk of freezing. Those are just conditions that you have to think about, as well as air transport. Where's your manufacturer or point of manufacturer to where the integrator is at? So all of those things from the unit level or box level manufacturing have to be done. And then on the rack and manifold side, same sort of thing. Where is that integration of the manifolds into the rack going to be done? Is that going to be done by the manufacturer? Are they both coming from the same place? Or is that going to be done by the integrator? So this paper does deal with all these potential different paths and each of the potential paths that you have to deal with and what those checks that have to be done through that or through those processes go.
So once the rack gets to the location in the data center, there's some things that happen on the facility side to prepare for that. One of that is a check on the facility side to make sure that the pipes are obviously clean and that the the flow of fluid that's coming to the CDUs that are feeding the racks are clean. There's usually filters installed, in the CDUs that protect the cold plates. So those have to be in place, an appropriate micron filtration for the level of the cold plates. And then on the CDU side, there's a primary filter that's going to protect the CDU from any filtration coming from the other side. So you got to make sure that you check those filters and are really prepared to fire that thing up.
Yep. So yeah, we'll talk about integration a little bit later, but I think the next sort of, as we were working through this with the ITE vendors, it was also infrastructure vendors such as Fred and myself saying, you're part of the transport equation now. It's not just PDUs that are in the back. There are liquid components, so you're part of this. So what risks do you see? And depending on the different vendors that you talk to, some try to ship their components, their liquid cooling components, filled with either a glycol or filled with a water or a pressurized nitrogen, and they all introduce different problems, and they mitigate different issues. From a transport perspective, from your time to manufacture to your time to delivery, will this be warehoused? Will it be warehoused for a week? Will it be warehoused for a month? Will it be warehoused for 6 months? That determines, can be a determining factor in what you're shipping it with. Glycol has great anti-corrosion and inhibitors in it. Has a good biocide protection as well. That chemical process can be maintained versus just putting water. Is it street water? Is it reverse osmosis? Is it DI water? Is it distilled? There are different classes of water and those recommendations, and a lot of those are up to the manufacturer. And from my perspective, I think consistency through the game is key. Water is sort of your baseline. Distilled would be best, but it's probably some of the harder to get in quantity. DI water is easier to get, but reverse osmosis is easy to do through filtration at a plant with city water. That sort of sets a baseline. Starting with propylene glycol, it's one of those, once PG is in the system, you can flush and flush and flush, and it's very difficult to get all traces of that out. So water, you're just adding PG to water, and that's typically not a problem. Some of the other pitfalls, though, with the transport is where it's going to be transported, time of year, climate, distance, and method of transport. A lot of air carriers just don't like it when things have liquid in it. They actually have regulations against it just because they don't want it to leak and damage other things. There's limits on volumes and limits on packaging as well. Essentially, they have to be packed for air shipment in 3x the packaging. The first 2 are to protect if there is a leak and contain that. If you're choosing to ship with gas, refrigerants are definitely a no-no. So it's very common to ship with an inert gas, dry nitrogen, or a forming gas that only has 5% hydrogen, but even that has limitations in terms of pressure. Road transport's typically good up till about, probably about 25, 28 PSI. Air transport, they typically don't like above about 14.7 PSI or 95 kPa. That's an IATA sort of regulation. You get around a couple things by shipping at that lower pressure, but it's harder to determine if your pressure is within tolerance for leak testing or component verification later without having to have, labeling the product as a hazardous material for shipping because it's a pressurized vessel. Sea freight can be subject to a lot of different temperature swings, but also longer time cycles. So all of these things have to factor into the decision on, okay, you've built the thing, now we need to get it somewhere, and that timeline and what methods you're going to go forward with how you do that. So yeah, transport isn't just, hey, call up UPS and come pick it up. There's actually a lot more involved in it, and when you get to some of the heavier things like CDUs, there's just a whole bunch of different challenges with that because the internal volume of it compared to a manifold can be so much larger. I'm not too worried about the volume in a single cold plate. If it leaks, it'll most likely be absorbed by the cardboard box it in. But a CDU gets shipped in a crate, doesn't really absorb water that well, likes to spill it out, but they hold so much liquid that a spill or a leak or anything in there is a problem. And then I'll finish this off and say by the time you get to the end of the transport cycle, you need to check it. prior to any other further work with it, you need to check it ahead of integration to make sure it's still intact and leak-free.
Yeah. The only thing I'll add on the transport is things can get damaged in transport. And just from experience in doing projects where we're building CDU systems with, we had a rear door project, and that the product actually comes from another country. So if you end up with a damaged panel or a part that you need to replace, I guess the advice would be make sure that you have pre-ordered your spare parts for anything and that you're prepared to deal with it, because any delay in transport or something that happens in transport, you know, the job finish date isn't going to care.
Yeah.
So I think a little bit of thought process that goes into, hey, I want to make sure that I'm prepared to receive it and install it is really critical.
Yep, that's a really good point. Even things like fittings, like things do happen, things get broken, but even things like fittings. So now we've got our transport, and we've got to integrate it. And when we talk about integration, now we're talking full rack integration. ITE could be in the rack, could have not been in the rack, but everything is integrated in the rack. Everything is now connected up. You have a single loop in, single loop out of a rack with multiple parallel circuits. What do? You know, I don't think it makes much sense at the rack level, the L12 or L11, L12 level to check each component individually, simply from a time thing. We're talking about scale computing here. I think it's, you know, and history and experience has proven that, you know, doing rack level checks, we know what those pressures are, we know what those gas pressure degradation curves are. Doing a simple pressure test with gas is always a good solution assurance that you don't have any major leaks before you put water in it. You want to identify those, we'll call them 0-day leaks, before you put water on and potentially wet something before you've ever powered it on. So there is, at the level of integration, the integration is done. What does that check look like? It is putting nitrogen on and looking for an immediate decay or putting some pressurized gas on, but it also is leaving it for some period of time and watching the pressure decay. There will be known decay rates that vendors can provide. Following that decay rate, if you're within an hour, over 4 hours, over 12 hours, you're good to put liquid on it. If you're outside of that, you know you probably have a slow leak. You might want to investigate that further. And the paper goes into a couple different ways. And one of the most common is using a forming gas, which is about 95% nitrogen, 5% helium, and using a hand sniffer to identify where that leak is at. You know, as you said, things can get damaged, and having spare parts, if it's something of replacing a QD, or maybe it's just because it's a dry seal, and when you add liquid to it, that will self-correct. Adding positive liquid pressure will allow the seals to adjust and settle and create that seal, but the hand sniffer will reveal where there's a leak. You'd want to know if there's a leak at a connector or a hose or a leak in the middle of a coil. Probably not going to want to use that coil. So it's at the integration step, there's more of these checks that have to be done, and then we're still not done. Once it's been integrated, especially if it's off-site integrated, we probably still should do some checks down the path. But it's now that the unit is integrated, do we charge with liquid and deliver to the end customer for deployment, or do we still leave it with a gas pressure charge and go to the end customer for deployment, and then transport comes right back into it?
Yeah, and just remember that integration process is also going to include some of the power components that go into the rack, because you might have to spin things up, so there'll be PDUs and power shelves that also go into the racks at the integration point potentially.
Yep. And then you get to the deploy stage. So at the deploy stage, okay, it's arrived. It's literally going to move feet or a few hundred feet. It's going to be carted. We're going to do one final check. We're either going to commission off the floor or we're going to commission on the floor. You know, there's benefits to doing both. There's drawbacks to doing both, and it's what's up to the end of the customer. But that gives you your final assurance that it's going to function. You know, at your integration level, you could be doing burn-in and setting your software packages and IPs and everything like that. And then you're ready for deployment. And once you go through that checks, these are what we've essentially laid out. Is there's 1,000 different paths to go down, but these are sort of the guesses and checks that you have to go through, so that when you do a deployment, it's a known, it's secure, it's safe. There's not going to be any leaks or those, you know, any components that need replaced. That's going to be managed. So you're not just putting water into something and crossing your fingers and hoping for the best, or liquid, we'll say, or refrigerant.
And I would just say if you've done all that right and you get it to the install stage, I would also take a look at our previous session on leak detection and
Yeah.
make sure you've implemented that leak detection section. So I know we're just about out of time.
Yep, so we'll just run back to, there's our chart. We've
that's the
checked the
chart.
boxes across the way, and that's for the most part, that, I would say blankly, that's as much as you can do. There is always sort of we know as much as we know going forward. The vendors will be able to provide the various components that make it up, their reliability information, compatibility information. We didn't even get into working fluids and fluid compatibility. That was out of scope for this, but all of these things, and assuming that the design was done with all that in mind, that's how we get to here for a successful deployment. So.
You don't mind at least?
Yeah, go
a
ahead.
question?
We'll open it up.
So John Mazzilli, so I've used some of the techniques in transport, especially with coils, and I've charged my coils with 3 times working pressure nitrogen and see if it gets there on time or gets there without violating. But I'm having trouble with some of the pressures that I'm using now. Can I use helium and use a lower pressure and still get a valid leak check?
You can. As one of the strong points, and I'll throw this out as from Invent, one of the strong points that we tout is not necessarily with coils, but with manifolds is helium leak chambers and testing like that. In terms of leaving it charged with helium, that's not our the way that we do it. We do charge with nitrogen to ship, but as far as pouring through all the transport, it wasn't spelled out that helium is an inert. It's not a problem. It's in significant concentration. It's not it is an oxygen displacement, but it's a non-hazardous, same as nitrogen. So the big problem that people have, especially with air transport, especially with something like a coil and higher pressures like the 3x pressure of that, is just that they're worried about bursting at altitude.
Sure. I understand the air side. In this case, it was just for more management. But the helium I was considering, because it's roughly molecules 6 to 7 times smaller than nitrogen.
Yeah.
So
there's a lot of leak testing that does, and those, we call it pinhole leaks with helium. It's one of those, okay, we found a leak. Where's it at? Is it really a problem? You're going to have some level of leaking at the connectors simply because the molecule size is so small. Okay. But what you're really trying to identify is the integrity of the coil itself intact.
Okay, thank you.
Yep.
And I think that's all the time we have.
Cool.
Let's thank our speakers.
Thanks, everybody.
Yep. Thank you, everyone.